that? Can you hear me okay? Okay. Alright, so let's get this going. Okay. So Dr. says we'll return sometime. For now, I'm going to finish up what Rahul started to discuss Tuesday, and then I'll go into a little bit of new material. And then we'll go on to a quiz. Okay, so what Rahul was discussing last time was sort of introducing centrifugal motion or centrifugal acceleration into our free body diagram. Right? And over here, if you remember, he ended up on that board, and he was starting to discuss a car going around some circular track. Alright? And he was saying that you have a car, and physicists can't draw cars, or draw cubes or squares. And it's going around at some speed d. Right? The asymmetry of my track will make sense to this. Alright, so the car is going around at some speed v, and this track has what we call a radius of curvature, r. Right? So if it's just a circular track, the radius of that circle will be r. But if it's just an oval track, that curved part has a radius of curvature, and that's what we're calling r. That's how sharply it curves. Alright. Now, Rahul had discussed this in some detail, and what he ended up, or what he was going to continue on with, was a slight variation of it, particularly this track having some sort of incline to it. There we go. Pull some Bob Ross stuff. Now this makes sense. Alright, so now the car comes up and is going around this embankment. Right? It's raised up so that the car doesn't fly off the wheel. Alright, and what I'm going to do is I'm just going to set up the free body diagram of this thing so that whenever you see this on the exam or quiz or homework, you know how to analyze it. I won't really solve any of the problems or I won't solve for any variables, but I'll give you the equation so that you know how to look at this picture. Alright? So as always, you start with your free body diagram. For those of you that are in my recitations, you know free body diagrams. You should know free body diagrams are the absolute necessity whenever you start a problem. For those of you that aren't, I'm sure Kevin has also told you this, but free body diagrams are extremely important. So for this particular scenario where we're interested in the car, and we'll say the car has mass m, then our free body diagram will be simply the car itself, and we're looking at this area, right? This is where we're looking. That's our free body diagram. So we know this is sitting on an incline. So I'll draw it in just for reference. And we'll say that the incline has some angle alpha. Right. The car has mass m, so we know gravity pulls it down. I'm getting used to writing with a big chalk. There we go. So it has weight, mass times gravity. It's also sitting on the surface, so it's going to have some surface force pointing directly out of the surface. Something like this. Alright. And, oh, likewise, this is a, as you want with your car, this does have friction in it, right? It's the friction between the wheels and the surface of the road. And let's see, this was discussed last time. Anyone point me in the direction, left or right? Which way is the friction going? Right. Yes, perfect. Right. Because friction always opposes sliding, right? So as the car is going around this embankment, if it's going to slide anywhere, it's going to slide to the left, which means friction is going to the right. So the friction is going to the right, and since it has to go along the incline, it's going right downwards. Alright, these are the forces acting on our car. Surface force, friction, and weight. Now for the net force. Alright? That's taking a little bit too much weight. Alright, what is the net force acting on us? Particularly, we have a special name for these types of forces whenever something's going around in a circle. What's that force? Centripetal. I heard someone whisper. Very good. Centripetal force, and centripetal force always, or centripetal acceleration, always goes towards the center of rotation. Right? This is towards the center of rotation. It's a horizontal direction. So our centripetal force is horizontally to the right. Okay? Alright, so there is our free body diagram. The only thing we have left to do is describe our coordinate system. Which way is our y, which way is our x. This will allow us to come up with our equations systematically so that we don't mess up our signs. Right? Now, on one of the homework problems, we look at something similar to this, block on an incline. And you choose your x-axis horizontal to the incline, your y-axis vertical. The reason you do that is because most of your forces are at some angle, right? So that keeps you from having to break all your forces in the complex. Here, this problem, you don't really benefit too much, right? This one is at an angle, this one's at an angle. These two are at other angles. So either way you want to do it, it doesn't really take you time also. But for those that haven't been playing with your rotated axes, I'll do it like this so that we get more practice. Right, so I'm going to set my positive x-axis to be down the incline, and my positive y-axis to be out of the incline. Alright. Now from that, all we have to do is sum up our forces in the positive y, and sum up our forces in the positive x. So all of our forces in the x direction, right? For those that are in calculus now, you should be familiar with this sign. It's the summation. We're just adding up a bunch of things. So sum of the forces in the x direction. With our x going down the incline, we have our positive friction, right? Friction is going down the incline. So it's going to be magnitude f. Right? And it's just the magnitude. We don't have to worry about sine or cosine. Because the way we've designed, or the way we've set our coordinate system, the positive x-axis, is parallel to that friction. Alright? And, let me draw one thing. Just as reference, remember this alpha, or that angle, is that angle. The reason I wanted to draw that in is because now we can very easily see that the weight also has a horizontal, or not horizontal in this case, an x component being here. Alright? And we know that x component is opposite to the angle, so we're not going to use cosine, we're going to use sine for the x component. Alright? And it's going also down the incline, so plus m magnitude g sine alpha. Alright. Those are the only forces acting in the x direction. So that must be equal to the net force in the x direction. One more addition. The net force is our centripetal force. Right, but our centripetal force is not parallel to our x or our y, which means we also need to break it up into components. So that's fine. Fortunately, with this setup, or this geometry, that's pretty easy. Right, because this line, we just draw a parallel line to that. Right, which means that this angle same idea as two parallel lines joined by some other line. These two angles are the same. You see that the same geometry is there, it's just displacement. So that we can use our alpha again to find the x component of that, which is just a to the c times cosine alpha. Right. There we go. There's our forces in the x. Now we do the same for our forces in the y. Our surface force is pointing completely in the y direction, and it's in the positive y direction, so positive surface. Our weight, or a component of our weight, is pointing in the negative y direction, so minus mg. Now we already used sign, so this one will be cosine. Right. Those are the only forces acting on our block in the y direction. So the only thing left is to get the y component of the net force, which is positive MAC sine. It is positive because if you tilt your head so that the x-axis is horizontal in your eyes, then you see that MAC is actually pointing slightly upwards compared to the x-axis. Alright, so there you go. There are the two equations, which whenever asked a question, like solve for the angle or solve for friction, these are the two equations you'll play with in order to find your variables. This is most of the work. Sorry. This is the physical work. The rest is algebra, right? Which is, in most cases, harder. So there we go. That ends our three-body diagram from last lecture. Right, before I move on, is everyone okay with this? No issues? Good. Alright, because now we're going into something completely different. Alright. That completely different thing is, this will take a moment to write out. Newton's universal Which here is where I put on the magnitude signs because they are in opposite directions, so they will be negative. Right? And Newton was able to figure out through help with Kepler and some data that this force goes as little m times 2. So that if you increase one of the masses, the force will increase. Divided by the separation distance squared. So if you found out that it goes with this, but in order to get the units right, in order to get the measurements right, we added some constant, capital G. Right? This is why we use lowercase g for graphing, because capital G is already there. Right? This is just some constant that's added in to make sure the units work out, and so that our numbers work out nicely. As G is the gravitational constant, it goes to where it's equal to, I think, what I remember, 6.67 times 10 to the negative 11 Newton meters squared per kilogram. This number is particularly important whenever you're talking about the hierarchy of forces, right? We have electrical forces, magnetic forces, and then we have nuclear forces. We also have gravitational forces. And it's the fact that this number is so small, it's times 10 to the negative 11, that makes gravity so weak. It's the weakest of our forces that we use. Right? So here we go. This is what Newton was able to figure out. And just as a little idea of what this does, if you're applying this, right, you go onto your calculator, your graphic calculator, you have one, and you plot this function as a function of f. G, so the magnitude of it, with respect to water. So you're separating the two particles at greater and greater distances. The force drops off very quickly. It starts off strong up close, but it drops off very quickly. So over here, the force is very weak. Up here, the force is very strong. In this case, strong is a relative term, right? Because I just said this is a very small number, so it's very weak in general. But in comparison to itself, it's strong up close, weak very far away. Right? This is why we have, say, our solar system. Right? Up close, all the planets are tightly bound, but as we scatter out, they're not so, they're more scattered. Right? Because as you get away from the sun, or the central massive object, the gravitational force gets weak. Okay. So this is gravity, right? We've already been talking about gravity. So now we need to see how it relates to the gravity we've been talking about. Because the gravity we've been talking about is just, it's not something complicated like this. It's just mass times 9.8 meters per second. So what I'll do is I'll look at it that way. Right? So consider a bit lopsided. Consider this is an up-close picture of Earth. Right? So that in this diagram, we're looking at this tiny sliver. This is Earth, and we're looking very close to it. Right? So this is the side of Earth. And we consider an object much smaller than Earth, of mass little m, and it's only at a height h off the ground. Right? So we have the Earth has some radius. Earth has some radius. Radius of Earth is about 6.4 times 10 to the 6 meters. And the moment we'll need it, the mass of the Earth is 6 times 10 to the 24 kilograms. Right? And for this argument, we don't really care the mass of the small. the radius, you have to be here. This is why I pointed out here. I was making a note. The radius r, or the letter r, that's the center to center distance, right? Which means down here, this is going to be the distance between the center of Earth and the center of our box up there, which means it's going to be the distance is radius of Earth plus h entirely. So this is how you would look at it here, right? So if you were to be discussing a rocket up in the atmosphere, this is how you would do it. You say the radius of Earth plus how high up off the ground the rocket is. Alright, so this is just perfectly fine general idea. Now we're going to place the restriction. If the radius of Earth is much, much greater than h. That is to say, our height off the ground is relatively small, right? We're a few feet off the ground, we're a few meters, and we're even a couple hundred meters off the ground. What I'm about to do is a little longer. These are all the scenarios we've been looking at, right? So if we're pretty close to the ground, then this equation becomes very nicely. I'll put a little squiggly up there. Right? It's a very simple thing, right? 1,000 plus 1 is roughly 1,000. That's the same idea here. The radius of Earth is extremely large, plus a few meters isn't going to make a big difference. So we can approximate it just right. Alright, I'm going to factor out n, so I pull them out. And I'm just going to put in some parentheses around g. And is at this moment that I realize I have not been recording, so the audio up to this point is going to be just terrible. There we go. 20 minutes in, it's not too bad. All right, back to this. All right, so now that we factored this out, all you gotta do is plug in G, plug in R, and plug in M. And this number very beautifully comes out to, as you might have guessed, 9.8 meters per second squared. If you're accurate in your numbers, it comes out to a few more decimal places, but that is what we've been discussing as gravity. So what you see is we haven't actually introduced anything new. This is what we've been discussing already. We're just generalizing it so that we can talk about things up in the atmosphere. Now we're no longer bound to surface experiments. Very nice. All right. Okay. But you see here I factored out little m. This gave me the acceleration on my small particle little m as 9.8. But from Newton's third law, right, every force has an equal and opposite force, which means that, as I was saying up here we discussed the force on little m due to big M. Likewise, we can look at the force on big M due to little m, where we're still talking about the mass of the planet. All right, so we do the same thing. The only difference is that instead of factoring out little m, I'm going to factor out big M. All right. You see, mathematically, these are equivalent equations, right? It's just the order of operation. If you were to do this, assuming the mass of this little m is, say, mass of an average human, about 80 kilograms. Or if you're vegan, it's about 20 kilograms. So if you plug in all the numbers again, we're not plugging in mass of Earth, we're plugging in the mass of just an average person, you would find that this is roughly 83 times 10 to the negative 23 meters per second squared. This is the acceleration that you as an average person is causing the Earth to go towards you, right? But the fact that you're so small compared to the Earth, we could get all the humans on the planet, set them up in, there's a lot of them in India, so we'll just save time and we'll push them over to India. All right. So if we get all the people in the planet, go to one location, even that number, which is a few billion, maybe 100 billion, wouldn't put a dent in this, right? So the Earth would barely even notice if humans were all collected in one spot, or if there were no humans at all, right? So even though you do have an effect on the Earth, it's pretty minuscule. I hope that doesn't depress you for the rest of the day. All right. There we go. So now we've been introduced to the force of gravity, right? It goes as this 1 over r squared behavior. It drops off very quickly. And all you got to do is, as long as you know the masses of the two objects interacting and the separation, you can calculate how strongly they interact. But now what we want to do is we want to relate this to the previous idea that we've been talking about. Not so much a car going around a racetrack, but centripetal acceleration. Whenever we relate these two things, something very nice is going to come out. All right. So what we'll do is consider the sun, some light radiating off. And around the sun is, as normal, a planet or a satellite going around it in some circular orbit. We'll stick to circular orbits for now, even though in general they're ellipses. Circular, it's going to be easy, but what I'm about to do in the end result will apply perfectly fine to elliptical orbits. All right? And our planet is going to go around on its orbit at some speed v. And we know how to calculate this speed v. All we need to know is how long it takes to go around the sun, i.e. a year for the Earth, and we need to know the distance between there. And then we can calculate the distance with the circumference, and the period will be how long it takes to make that distance. So distance over time gives us that speed. And we're going to analyze this knowing that this is our separation. And we'll do it exactly as we've been doing before with our free body diagrams. Oh, and for bookkeeping, I'll say this is, the sun has mass m, this planet has mass little m. All right, so our free body diagram on our planet is going to look something like this. Right, we have our planet. Gravity is pulling it towards the sun. It's pulling it towards itself, like we just discussed, but the sun is massive. Planets are usually pretty small, so we're going to just pay attention to the forces on the planet for now. All right, so we know gravity is pulling that planet towards the sun. Right, so we have a force of gravity down at an angle like that. If I had been a little bit more cautious and forward thinking, I would have put the planet up here so that my gravity would have gone straight down. But now that we know how to rotate our coordinate systems, this shouldn't be an issue. All right, so gravity is pulling it down. We're in the vacuum of space. We don't really have to worry about friction or anything for the most part. So This is the only force acting on our planet. And since we're going around in some circular motion, we know that the net force on this thing, on the planet, is some centripetal force. Just like our argument over there with the car. The thing is going around in a circle, so the net force is some centripetal force towards the center of rotation. Center of rotation is the sun, so we're pointing towards the sun. All right, last thing we got to do, as usual, just for bookkeeping, name your coordinate system. So we'll say this is the positive y direction. If you were introduced to, say, like the radial direction or anything like that, I would use a wiser choice of letters. But for now, we're not really going to use it. Just we're going to use it to make sure our signs are proper. All right, unfortunately, everything is pointing in the same direction, which means that although the way we're looking at it is at an angle, we don't have to worry about any angles, no cosines or sines, right? Everything's pointing in the same direction, so that our free body diagram gives us a sum of forces in the y direction as F of g. That's the only thing acting on it, so that must be equal to the net force. Right? Very simple argument. So here's where the fun starts. All right? Because we know what this equation is. This equation is that one there. So we just plug that in. G, our gravitational constant, it doesn't change. Hopefully. Our two masses interacting, mass of the sun, mass of whatever the planet we're looking at, divided by the separation distance, squared. All right, that's the left-hand side. The right-hand side is our little mass m times centripetal acceleration, which goes as v squared over r, the radius of curvature. And since in this case, the sun is sitting at the center of our radius of curvature, or the center of our circle, then the separation distance and the radius of curvature are the same. We don't have to worry about them being different. All right, so we see our little m's cancel out, which is nice because that means what we're about to do is completely independent of what planet we're looking at. Right? It's only dependent on how far the planet is, so it doesn't matter if we're looking at a rock that's floating by Earth. As long as it's the same distance from the sun, the thing I'm getting to will apply perfectly fine. All right, and we'll rearrange just a little bit. Particularly, I'll solve for v. All right, so I pull r over. I multiply both sides by r. That gets me g, m, r comes over. Cancels out one of those. So gm over now just r is equal to v squared. Or take the square root. With plus or minus. And you get that v is now equal to the square root plus or minus the square root of gm over r. And we don't really care about signs for this part, so I'm just going to say the positive side. Right? The negative will do just fine, but it's only going to cause unnecessary complications. All right, so v goes as the square root of gm over r. Oh, actually, that'll save some time. There we go. Forgot about this one. All right, so we have v goes as square root of gm over r, but we also know that speed is equal to just the distance divided by time, right? And as long as we're talking about the time that it takes for the thing to go a certain distance, then this equation will work perfectly fine. So if we say the distance is the circumference of the orbit, right? If the distance is the circumference of this orbit, then we know that circumference for a circle is 2 pi times r. The amount of time it takes to make one of those orbits is just the period. All right? And for those of you that aren't quite awake just yet, or have already gone back to sleep, the period for Earth is a year, right? On these problems that we'll give you, you will have to use some intuition about these sorts of things, right? The period of one Earth orbit is 1 year, by definition. All right, which means that v, there's nothing on the right-hand side of that. Our speed v, which we just found, is also equal to 2 pi r over t. So by equating the two, so I'm going to plug this onto the right-hand side of that. Okay. Square both sides so that we get rid of this nasty radical. No one likes radicals these days. You get gm over r is equal to 4 pi squared r squared over t squared. Now I gotta erase the book. Okay, now that we have that, we're just going to rearrange a little bit, and we find by multiplying both sides by t squared and both sides by r. All right. Now on the right-hand side, it's r cubed, right? Because we already had r squared over there. We're multiplying both sides by an r, so that raises it up. Finally, the last bit. T squared, by dividing both sides by gm, is equal to 4. Oh, that pi should be squared. Four pi squared over gm times r cubed. All right, in parentheses here, we just have a constant, right? It's just a constant. You compute it once, you memorize it if you want. It's just fine. The important part is this relation here. T squared is proportional to r cubed, right? This is proportionality, not the Greek letter alpha. That just means that these two are related by just a constant. This is Kepler's third law. This was one of the beauties of what Newton did with his law of gravity. Kepler was able to use some extremely accurate data obtained by some guy with a golden nose. He was able to obtain extremely accurate data, and from that data he was able to come up with 3 laws of planetary motion. All right, that was based on experimental data. Sometime later, Newton was able to come up with an equation for gravity, which, under careful mathematical or algebraic manipulation, he was able to derive exactly what Kepler came up with, right? But now he was able to come up with the exact numbers that relate the two. So it was a pretty nice deal. All right, so before I go on, I'll just give you a quick summary of the three main things that the law of gravity touches on. I'll deal with that later. Whew. All right, so in summary, so if you take anything away from this past 40 minutes, Newton's gravity has a magnitude calculated by G m over r squared. Right? If we're considering we're close to the surface of Earth, we don't have to worry about this. We can just use mg, right? But whenever we're talking about planets or things interacting that has a separation much greater than the radius of Earth, then that's the one we use. I don't really have to write this next one since I just said it, but near surface of Earth, this is what astronomers call Earth. It's just a symbol they use, so they don't have to write it all the time. So near surface of Earth, Fg goes back to what we're familiar with, m times g, 9.8. And finally, in gravitational systems, that is to say, in systems of particles that has gravity as the main force deciding where all the particles are going. For the simple scenario of just one object orbiting another object, the period of the orbit, so how long it takes to go around, square that, is equal to some constant times the cubed radius of their separation. All right, so these are the three main things to remember here. Of course, and also your familiarity with the equation so that you can play with it algebraically. So these are the main ideas. All right. Now, I work in cosmology, so gravity is like my baby. I love talking about it. But unfortunately, in this course, this is about as far as I can go in describing to you what's gravity, the importance of gravity. So I'm going to make another change of gears. I'm going to go to something completely different. 101 is a fast-paced course, so this will be our third topic on this lecture. Not bad. On the bright side, whenever you go on to any of your other gen ed courses, they'll be extremely easy, right? You'll breeze right through history and philosophy like they were nothing. All right, so now we're leaving gravity almost entirely. We'll still have it in the back of our thoughts, but now what we're going to do is talk about the idea of work. All right, this is not exactly the type of work that you're used to discussing, like I'm going to go do homework or I'm going to go to my job at Quiznos and work. Right? This is the physical, mathematical use of work. Right? Precisely It's the energy required to move something from A to B. All right, and what I'll do is I'll give you the general mathematical definition of it. And with practice and playing with problems, you'll get more of a fundamental understanding of what it's going to be. So work going from point A to point B, right? This is equal to magnitude of F. I'll give you a diagram in just a moment so you understand what all this means. Magnitude of F times magnitude of X times cosine of theta. If you're familiar with calculus or vector algebra, you'll also recognize this as F dot X, a special type of multiplication with vectors. But if you're not familiar with the dot product, don't worry about that, right? I mention it only because you will see it in places, and just know that this is equal to magnitude times cosine theta. You can almost entirely forget that last bit if you need. All right, and what I mean by this, okay, is if you have some object, we'll say, we'll have an object here at point A. All right, and we want to move it to point B. Oh. All right, it's a very simple idea. Move object from A to B. In order to move it from A to B, assuming the object, say for simplicity, is at rest, in order to get it from here to there, you have to apply a force to it, right? It's going to change velocity, so therefore you have to apply a force. And let's say for arbitrariness, or for generality, you apply the force in this direction. All right? So that's the force you apply. For some reason, maybe you're not that smart. But the distance you're actually going to go, the distance the object is going, is from here along this path to here. So this will be our x, right? X, as we've been using previously, it's a measure of distance, but now it's a vector because now we're worried about the direction of that distance that we're going. All right, so we're going from A to B. They're separated by some number, some magnitude, and in this direction. The angle theta that I discussed, or I brought up, is the angle that lies between these two vectors, between vector f and vector x. So now that you have the geometry, the idea plotted out, now this equation, at least mathematically, is very easy to play with. You take whatever number we give you for the magnitude of f, whatever number we give you for the magnitude of x, multiply them with the cosine of the angle between them, right? So this is the general idea. And as you move along this path, as long as f is constant, so you keep the same magnitude and the same direction, I'm changing slightly direction, but you know what I mean. Then the total amount of work to go from A to B will be calculated exactly from this. Okay? The important part is that this is assumed as a constant force, at least along the path that you're interested in. If it's not a constant force, if it's changing with how you go, right? If you're getting tired as you push the box along, then you'll have to do this with an integral which no one wants to do that. Even I don't particularly want to do that. All right, so if we stick to a constant force along the path, then this nice simple equation will do perfectly fine. All right, so as I said, I'll give you just the general equation for it, and now some examples will paint a clearer picture of exactly what this is. All right. Oh, before I go on, one small detail about this equation. Not particularly about the equation, but about work, right? Because this is now the first introduction of what we call energy. Right? Energy, everyone uses it all the time in normal language, but here, energy has particular units. So the units of work, we can guess from our equation here. Force times distance times some number. So the units of this will be units of force, which are newtons, times units of distance, which is meters, which we define Newton meters as J. Right? This is what we call a joule, or if you have multiple of them, joules. Some French guy or whatever, some guy that was important for something. His name was Jules. He did some work relating to energy, and that's what it is. I'm not particularly good on history. Dr. Sin is phenomenal with it, so he'll be able to discuss more on the origin of this guy Jules, if he so chooses. Okay, so as I said, now to play with this equation, but in systems that we've looked at before. So we'll go back to our nice block sitting on some sort of surface. All right, and for now I'll take this surface right? I'll say the surface is completely smooth, so zero friction. Okay, so the box has some mass m. Oh, actually we don't care about the mass m. All you really care about for now is that you apply a force on it at some angle, as we've been doing. That angle measured from the positive x-axis is theta. And say you want to move a distance, so from A to B. Of 10 meters. And just for mathematical or arithmetic's sake, we'll say theta is equal to 60 degrees, and the magnitude of your force is 5 newtons. All right, so magnitude of force, angle theta, distance 10 meters. All right, so if you want to calculate the work, how much work will it take to go from here, point A, to here, point B, work A to B is simply just write down the equation, then plug in numbers, right? Just as someone who grades the quizzes and the exams, writing down the equation does save a lot of time for those grading it, right? If you just write down numbers, we have to spend a little bit of time trying to figure out what you're saying. So just as a common courtesy. All right, so F is 5, X is 10, cosine of 60. Let's go cosine of 60, anyone? 0.5 or a half, perfectly fine. All right, very good. All right, so 0.5 times 10 is 5, 5 times 5 is 25. This is newtons, right? Newtons times meters, which we just found out was this new unit called joules. So that's how much work it would take to go from A to B, right? To take a box, push a box, some force of 5 newtons at an angle of 60, a distance 10 meters. I understand this is a new unit. You don't really know how to approximate it. You're not familiar with it. So just to put it into some perspective, 1 baked potato. One baked potato is about 700,000 joules, assuming you eat the potato. There we go, got that one backwards. All right, so if you eat the baked potato, you get roughly 700,000 joules of energy from it. All right. So 25 joules is nothing. You can do that all day. All right, so that's the simple case. Now I'm going to add one slight difficulty, just to show you an important part that will cause you troubles if you're not careful about it. So all I'm going to do is I'm going to take the same system, right? Same block, same force, same angle, and the same distance. All right, so these numbers are going to be the same. The only thing I'm going to change is to say that this is now a rough surface. Right? Sorry, I was pointing up here. All the numbers are the same here. The only thing I'm changing is from frictionless to rough, which means now we're going to have to worry about friction. And it won't really plug in numbers. One, we're close to being out of time, and two, because it just gets a bit nasty if you do it entirely. All right? So what we want to do is calculate, again, the amount of work it goes from A to B. So you start out with a simple definition, or you start out with noting that the amount of work to go from A to B, since, where is it? This is our definition of work. There we go. That's our definition of work. For every force, you'll have some amount of work related to it, right? So the net force will be the net amount of work, or you can just calculate the amount of work done by each individual force and add them together. That is to say, the work to go from A to B is equal to the work done by your force F plus the work done by friction, right? Because friction is also applying some sort of force to your block. There's also all the other forces, such as when you do your free body diagram, your surface force, your weight, the friction, as I just said. But there's a nice simple relation or a reason why those don't come into play. The reason is because we are going this way. The work is proportional to cosine of the angle between them. The angle between this direction and this force is 90 degrees. Cosine of 90 is 0, so that they don't contribute any work, right? They are perpendicular to the distance gone, so they don't contribute any work to going from A to B. All right, so now to go on to this. So the work done by your force applied, it's the same idea. F x cosine theta. We're not changing any numbers, so that term is going to be the same, right? It's going to be the 25 joules we found before. Right there. Right? That number is going to be the same. What's new about this is this guy here. I don't really know, I didn't give you enough information to calculate what the frictional force is, right? I didn't tell you the mass or the coefficient of friction, so you don't know what that is. But that's not the important part here. The important part is what is the angle between the two. And I won't really ask you about it. The distance is this way, right? This is the way we're going. That's the direction of x. But the direction of our frictional force is opposite to that, which means the angle in between them is not some small angle theta, it's 180 degrees, right? For those that can't see because of this, that's 180. And cosine of 180, real fast, what is it? Cosine of 0, how about that? 1. Cosine of 180. Minus 1, exactly. Which means that our total work, now that we're introducing friction, is going to be the 25 that we found before, but now minus some number. So you can have negative work done, right? And it's not just friction, right? It's not just friction that does negative work. It's any force that's applied opposite to the direction of motion. That is to say, if someone drops a big block on you and you try to catch it, but it's too heavy for you to actually stop it, you are applying a force that's upwards, right? You're trying to stop it, but gravity is too much and it's pushing it downwards. The motion is going downwards, you're applying a force opposite to it, so the force that you apply can also be negative. All right, so there we go. That is all I have for you. If you have any questions, we'll talk about it after the quiz. So for now, clear off your desk.